This presentation explores different energy storage technologies with a special focus on vanadium flow batteries. This topic will be presented by Liam Bowie, Adam DeNise, and Connie Morino.
First, we'll give a brief overview of the flywheel, thermal, and the vanadium flow energy storages, followed by a more in-depth discussion of how V-flow batteries operate.
Exploring new energy storage technologies are important for several different reasons, depending on the restrictions and purposes of the consumer. Key factors when optimizing energy storage technologies include cost, environmental concerns, size constraints, necessary efficiencies, and resources available to the consumer. We'll start our brief overview with flywheel technologies. Flywheels can use electrical energy input stored as kinetic energy of the rotor as designated in the diagram. The rotor spins with minimal friction, allowing that kinetic energy to convert to electricity. Next, we'll explore thermal energy storage technologies. Thermal storage allows us to temporarily reserve energy produced in the form of heat or cold for use at a different time. Many different forms of thermal energy technologies exist, such as solar or molten salt. Thermal energy is produced during periods of off-peak electrical demand. The energy is collected in a thermal energy storage tank and then withdrawn and distributed to the facility. Finally, we'll focus on vanadium flow batteries. Vanadium flow, also known as V-flow batteries, can offer almost unlimited energy capacity simply by using larger electrolyte storage tanks. In contrast to other batteries, such as lithium or lead acid batteries, which use two different chemicals exchanging valence electrons, V-flow batteries use multiple valence states of just vanadium to store and release charges.
Looking at the V-flow batteries, it is a highly anticipated energy storage technology due to many reasons, such as it being non-flammable, recyclable and reusable, compact, and fully containerized. Looking at the inner workings of the V-flow battery, V-flow batteries allow for the maximum optimization due to their separate power and energy source. This independence allows the V-flow battery to be manipulated to the output of energy and/or power source without affecting the other per the consumer's needs. Along with optimizing the delivery of the power and energy source, V-flow batteries operate on only one source of element, which in this case is vanadium, and this results in semi-infinite cycles without sacrificing the cycle time over the years, unlike other batteries. Looking at the main components of a V-flow battery, we first have the output source that gives the consumer the electricity. We then have the power cell where the energy is being converted. And last but not least, we have the storage tank where extra electrons are being circulated for continuous use. Now we go into detail of how each of these three components work. First, we have the power cell, where the positive and negative valence electrons get transferred back and forth from each other in each half cell in order to generate the electricity. Then, we have the electrolyte tanks, where the extra vanadium electrons are stored for energy, which are ready to flow into the power cell depending on the amount of electricity needed for the consumer. Lastly, we have the part of the battery where energy is being converted and outputted from the AC and DC motor source, such as electricity.
Since lithium-ion batteries are currently dominating the market, I will compare them to vanadium flow batteries. Starting with applications, vanadium flow batteries are most useful in load leveling and peak shaving. Load leveling is a technique used to store power during off-peak times and deliver power during high demand on the grid. Peak shaving is similar but is used for reducing the peak demand. This benefits solar and wind systems whose power generation can vary greatly throughout the day. Lithium-ion batteries have the same applications but are optimal for mobile use. Now onto the performance of each. Vanadium flow batteries have a longer discharge time and life cycle and can be reused and recycled. Vanadium flow can also be recharged and discharged at the same time. Although lithium-ion batteries have a higher efficiency, it has a significantly shorter lifespan, making the option of vanadium flow batteries very lucrative. Cost is important to consider. Currently, lithium-ion batteries are cheaper, but the prices of both are predicted to decrease, and vanadium flow batteries might become competitive in cost in the near future. Vanadium flow batteries are best used for larger operations because only the tank size has to increase, thus decreasing the cost per kilowatt hour, whereas lithium-ion batteries' cost will increase for larger sizes. Since cost is such a large driving factor, manufacturing and resulting environmental impacts are often overlooked to some extent. Vanadium is extracted as a byproduct of mining and minerals processes. Lithium batteries are mainly made up of lithium, cobalt, nickel, and graphite. Obtaining these materials has been known to cause environmental and child labor issues. These two charts show the current costs and predicted improvements for various batteries and focus on the specific areas of vanadium flow batteries. For example, the calendar life, efficiency, and costs are all expected to improve significantly for vanadium flow batteries. Tesla recently constructed a 129 megawatt hour lithium ion battery in South Australia. This made major headlines because it is the largest battery in the world used for energy storage currently, and it serves power to 30,000 residents for 1 hour. However, little has been covered on a current project in China where an 800 megawatt hour vanadium flow battery is being built to serve 7 million residents and peak shave 8% of the load in that region.
Thanks for watching our presentation on energy storage technologies and V-flow batteries.